Hi everyone, it's Miss Phelan here. First, I just want to say congrats for making it to the last week of remote learning. This is going to be the last week that we have new learning materials. You guys have been working so hard and doing such great work on your own. I hope that you know I'm proud of you. So let's kick off the last lesson that we will do together in Earth Science. In this lesson, we are going to talk a little bit about geologic history, exploring Earth's past. Okay, how do we know what we know about Earth's history? Humans weren't around long enough we've only been around for just a very, 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 very tiny portion of Earth's history. So how do we know what happened before humans, before animals, before life at all? So one thing that we know about Earth's history is the age of the Earth. The Earth is 4.6 billion years old. Okay, so in these pictures, we can see what scientists think the Earth looked like billions of years ago, 4 billion years ago. Okay, so scientists have been able to create these images that kind of recreate or provide a picture of what the Earth might have looked like. 4.6 billion years ago, it was probably just a really hot ball of molten rock, hot magma, okay, like we see in this picture here. There was no land, there were no oceans, it was just a hot ball of volcanic activity. In this recreated picture here, we could see some of the volcanoes that might have been on the surface of the Earth. We see there are a lot of meteors or asteroids striking the surface of the Earth. There was no atmosphere. There was nothing to protect the surface of the Earth. So it got hit with a lot of objects from space. And 4.6 billion years go by, and we go from this to our beautiful planet that we have today. Right now, we are able to go into space and see our beautiful planet from up above. There are two American astronauts in space right now, looking down on Earth, doing some research to learn a little bit more about our planet. So, Earth is 4.6 billion years old, and most of Earth's history went by without life on the planet. Okay, 4 billion of those 4.6 billion years ago, 4 billion of the 4.6 billion years went by without much life on the planet. It was mostly just rocks, volcanoes. Okay, there were some microbial life, little tiny microbes, bacteria, viruses that might have existed back then. But for most of Earth's history, there were no animals, no plants on the planet. However, around 542 million years ago, this changed. This is when we had what we call the Cambrian explosion. In the Cambrian explosion, diverse organisms evolved in the oceans. Okay, life started to form, multicellular life, large animals started to come about. I shouldn't say animals, large creatures, large organisms of all different species started to evolve and develop on the planet. More time goes by and we get to what we call the Mesozoic era. This is an era we like to think about, which is why I wanted to highlight it here in this video. We won't talk a lot about all of the different periods of Earth's history, but the Mesozoic era is what we know of as the age of the dinosaurs. In this time period, right, there was a lot of diversity on the planet, a lot of plant diversity. Okay, we usually are more excited by thinking about the different animals that might have existed then, but there were a lot of plant diversity in the Mesozoic era, and those plants helped to support the dinosaurs, right? Because they ate plants. Some of them were herbivores eating those plants. So that diversity helped the dinosaurs themselves, okay? And the dinosaurs lived for a very long period of time in Earth's history, living all over the Earth. But we don't see dinosaurs today, right? What happened? Well, the dinosaurs died in what we call a mass extinction event. What is mass extinction? First, let's think about the word extinction a little bit. Okay, extinction or extinct means that a specific species of plant or animal is no longer alive. All of the individuals in that species have died so that they can no longer reproduce and make more babies, make more plants. So the species itself goes extinct. There are no longer any dinosaurs because they have all gone extinct. Back to this phrase mass extinction. A mass extinction is an event that causes a large numbers of species to go extinct within a relatively short period of geologic time. Okay, so a mass extinction, a large number of species went extinct. It wasn't just one type of dinosaur that went extinct. It wasn't just one type of plant. All of the dinosaurs went extinct. A lot of the plants went extinct. It wasn't just one specific species, but a lot of the species, all of the dinosaurs, most of the plants that lived in that time. All of these organisms, all of these species went extinct. How did it happen? Well, 65.5 million years ago, scientists believe that a large asteroid or a giant rock from outer space hit the Earth near the Yucatan Peninsula in Mexico. Okay, so the Yucatan Peninsula is that part of Mexico that kind of sticks out like a foot. And in this area, scientists have found a lot of evidence. They found the crater of what they believe was an asteroid or a giant rock that hit the Earth about 65 million years ago. And this event appears to line up with when dinosaur bones are no longer found on Earth. One important thing to remember is that a lot of people tend to think that the giant asteroid hit the Earth and killed the dinosaurs in that area, right? They think that the dinosaurs themselves got hit by a giant asteroid. But that's not what happened. It wasn't the asteroid itself that made the dinosaurs go extinct. What happened after the asteroid hit the planet was that it ejected or sent up dust into the atmosphere that changed the climate on Earth. Remember, we learned a few weeks ago in one of the videos that when a volcano erupts, it can change the climate on Earth because the dust goes into the atmosphere and blocks the sunlight from reaching Earth. The same thing happened with the asteroid. The asteroid ejected dust into the atmosphere and blocked the sun. Without that sunlight, many plants weren't able to survive. Plants need sunlight. Many plants went extinct, and without those plants, there was no food for the dinosaurs. that some of the animals might have just not been able to adapt to the changing in temperature too. So in this video, we're learning about geologic history. I just told you that the Earth was 4.6 billion years old. I told you that 65 million years ago, we think that a giant asteroid hit the Earth. How do we know these things happened so long ago if we weren't around to see them? How do we know how old the Earth is? There are two ways that we can take a look at all of the rocks on Earth, all of the fossils, and put information together to figure out how old these rocks or these fossils are. The first way, so this is one of our vocab words, is called absolute dating. Absolute dating is a scientific process or a scientific method that tells us the actual age of a rock or fossil. The actual age. So this would be like saying this rock is 3 million years old. To find the actual or absolute age of a rock, geologists measure the amount of radioactive material left in a rock. So kind of like you can think of a radioactive substance and maybe some kind of sci-fi movie or superhero movie. Okay, there is radioactive material in rocks, and by looking at how much of that radioactive material is there, scientists are able to figure out exactly how old a rock is. The second way of figuring out how old rocks are is from what we call relative dating. Relative dating is when we compare the age of one rock to another rock. This is a little bit easier. In this case, instead of saying a rock is 3 million years old, you can just say this igneous rock is older than that sedimentary rock. You're just comparing the age of the two rocks. So, for example, if we look at this picture, here are different layers of rock underneath the ground, okay? And in each layer, here at the top, it says younger, and then down near the bottom, it says older. So in relative dating, we would just say this rock up here is younger than this rock at the bottom. Let's compare these two forms of figuring out how old a rock is. Absolute dating was the first thing we learned about, and that would be like saying, my dog is 8 years old. Or, this rock is 3.5 billion years old. You're giving a specific number. You know exactly how old that rock is. In relative dating, you're comparing the age of two rocks. So you might say, my dog is older than your dog. So your dog must be younger than 8. This rock is older than that rock, so this rock must be more than 3.5 billion years old. You're just simply comparing. We don't know exactly how old this new rock is, but we do know it's older than the other rock. The last thing we're going to learn about here as we talk about relative dating and thinking about how old rocks are is what we call the law of superposition. Okay, in the law of superposition, this is a law that geologists use when they're trying to investigate how old different rocks are on Earth when they're trying to recreate geologic history and figure out what happened on Earth before we were here. And this law, this geologic law, says that the oldest rocks are on the bottom and the youngest rocks are on top. So, for example, if you look at a few layers of rock in the Earth, here's the sky up here, here's the grass, and as we start digging down into the grass, we see a few different layers of rock. The oldest rock is on the bottom. Then this layer is a little bit younger. This is younger. And then the youngest layer is on the very top. You can think of it like laundry in a laundry bin in your bedroom. The oldest laundry, the clothes you wore the longest time ago, are at the bottom of your laundry basket. And the clothes that are the youngest, or the clothes that you wore most recently, maybe the clothes you wore yesterday, would be at the top of the basket. It's the same for the rocks. The oldest rocks are at the bottom. The youngest rocks are at the top. Okay, here's another picture of the law of superposition. Here we're saying that the oldest rocks are at the bottom. The youngest rocks are at the top. And in this picture, we can combine the law of superposition, relative dating, and absolute dating to try to figure out exactly how old some of these rocks are. Okay, so we know the oldest rocks are at the bottom, the youngest rocks are at the top. Now, if absolute dating tells me that the rocks at the bottom are 140 million years old, and the rocks at the top are about 120 million years old, well, I don't know exactly, but I can guess that maybe this rock in the middle is somewhere in between. Maybe this rock here is about 130 million years old, right? 130 is in between 120 and 140 million years old. And I can't say for sure, but by using both absolute and relative dating together, I can get an estimate of how old this rock is, even if I can't figure out exactly how old it is. Okay, and we can see this in real rock layers, real rock strata on planet Earth. Okay, in this picture, you can see some of the different colors, some of the rock layers in this rock formation. Okay, I'm going to erase that so that you can just look at the picture. But with the law of superposition, we would say at the bottom, we have the oldest rocks, and near the top, we have the youngest rocks. Again, in this picture, old rocks are near the bottom, and the youngest rocks are near the top. In the middle, you have many different layers, and those are somewhere in age between the oldest rocks and the youngest rocks. When we show this on a test question, it might look like this. In this picture here, we have 3 different rock layers. We call the top rock layer L, the middle layer K, and the bottom layer J. Let's think about what we know and try to figure out some information about these rocks. Well, let's think which rock here is the oldest and which rock layer is the youngest. The oldest rock layer we learned is at the bottom. So here, the oldest rock layer is rock layer J. The youngest rock layer is at the top, and the youngest rock layer is layer L. So what if I told you that rock layer K in the middle here, rock layer K was found to be 200 million years old? How old is the rock in rock layer L? Well, rock layer L would have to be less than 200 million years old because rock layer L is on top of rock layer K. So if it's on top, we know it must be younger. So rock layer L must be less than 200 million years old. Let's try another example. In this, what we call outcrop, what is the oldest layer? What is the youngest layer? Well, the oldest layer is on the bottom. So here, my oldest layer has to be layer G. The youngest layer is on the top. So the youngest layer here must be layer I. Let's do another problem. If rock G is 400 million years old, and rock I at the top is 100 million years old. It's younger. How old is rock layer H? Well, if rock layer G is 400 million years old, rock layer I is 100 million years old, rock layer H must be somewhere in between. So in this case, it could be anywhere between 100 and 400 million years. I will pick a number in between these two numbers. So I might say rock layer H is about, let's say, 200 million years old. Okay, so let's just end our video here today by taking a little bit of notes that will help you with the exit ticket questions. So please take out a piece of paper and write down these notes. They'll help you as you go through to do the exit ticket. So our notes are on geologic history. Let's write down a few important things. The Earth is 4.6 billion years old. A lot of things happen in Earth's history, but in this video we talked a little bit about the dinosaurs. So the dinosaurs died in a mass extinction event. A large asteroid hit Earth about 65 million years ago. We also talked about, how do we know this? How do we know these numbers? We obviously weren't around when the dinosaurs were around. We weren't around when this asteroid hit Earth. What are ways that we can learn how long ago these events happened? We have two ways of trying to figure out the timeline of geologic history. One is through absolute dating. Absolute dating tells the actual age of a rock or fossil. For example, a rock A is 3 billion years old. We can also use what we call relative dating, and this method compares the age of one rock to another rock. Example would be to say rock A is older than rock B. And we can apply the ideas of relative dating with what we call the law of superposition. If we have a few different layers of rock, okay, the oldest rocks are on the bottom and the youngest rocks are on the top. Thanks for following along. Don't forget to complete the exit ticket before you finish today.